Okay, so the act of using protons, this proton gradient, to synthesize ATP, we call the flow of protons chemiosmosis. So we call the flow of protons chemiosmosis. And it's this chemiosmotic gradient that is the fuel for producing ATP through this mechanism. You get about 30 ATP for every glucose molecule. Now compare that to the 2 ATP you get from glycolysis and the 2 ATP you get from the citric acid cycle. Actually, let me draw glycolysis happening out here. I don't want to confuse you. Glycolysis is happening outside of the mitochondrion. So you get 2 from the citric acid cycle. You get 30 thanks to this chemiosmotic gradient. So that's a huge difference. It's so important that this electron transport chain not get clogged. This is why if you stop breathing in oxygen, you die. Without oxygen, the chain cannot be cleared out. If the chain gets clogged, there is no more transfer of electrons. And if there's no more transfer of electrons, the pumping stops. This proton gradient wants to reach equilibrium, and it will reach equilibrium if it's not constantly being pumped against the concentration gradient, right? So if the pumping stops, then eventually all of these protons are going to rush in, and eventually we'll get to a state where the proton concentration is the same on both sides. Well, if that happens, the spinning stops. And if the spinning stops, ATP production stops. At least ATP production through the citric acid cycle and oxidative phosphorylation. That would be bad. Your cells cannot survive long-term from glycolysis over here. Glycolysis is an important stepping stone. But this evolutionary adaptation of taking glycolysis much further is absolutely essential, especially for a eukaryotic cell, which is much more complex. It has a much larger volume. Its energy demands are just so much higher than something like a prokaryotic cell. That's not to say that prokaryotic cells don't do this. They do this. It looks a little bit different because they don't have a mitochondrion. But prokaryotic cells absolutely can utilize an electron transport chain. They absolutely can utilize ATP synthase, but their energy demands are not as nearly as large as that of a eukaryotic cell. And so this is really important. This is why you need oxygen. Look at something like cyanide. Cyanide is nasty. Nitrogen in general can really mess up your mitochondria. This is why when you have nitrogen waste, when you break down amino acids and when you break down nucleic acids, that excess nitrogen that you produce needs to get flushed out, like literally flushed out. You pee it out as urea because a buildup of nitrogen can be toxic for this reason. Nitrogen likes to block the electron transport chain. I don't know if cyanide blocks complex 2 or it might be complex 3. I'm not sure off the top of my head, but the point is that if you introduce a compound that attaches itself onto the electron transport chain and prevents it from transferring electrons, then suddenly the electron passing game stops, right? So if complex 1 gets electrons from NADH, but it can't transfer it to complex 2 because complex 2 is being blocked, then suddenly pumping stops, right? Complex 1 can't pump because it can only pump when the electron flows. Complex 3 and 4 can't pump because there's no flowing electron. So what's going to happen to that chemiosmotic gradient? It's going to reach equilibrium. And if the gradient reaches equilibrium, the spinning of ATP synthase stops. And if the spinning stops, ATP production stops. And now the cell is in deep trouble. One last thing I want to mention. It is possible to uncouple the chemiosmotic gradient with ATP synthesis. All right, so think about what I just said. Uncouple. Remember, we had talked about energy coupling earlier. Energy coupling is just using an energy releasing process to fuel an energy consuming process. So, hydrogen ions flowing down their electrochemical gradient, that's an energy releasing process. Some of that energy is captured to make ATP. ATP production is an energy consuming process. So you take an energy releasing process and use it to fuel an energy consuming process. That's called energy coupling. But what I just said is that it is possible to uncouple the chemiosmotic gradient with ATP production. There are organisms that are capable of using, actually, let me draw it in red just to make sure you understand that it's different. There are organisms that are capable of using what's called an uncoupler protein. An uncoupler protein is exactly what it sounds like. It's going to allow protons to diffuse down into the matrix, but this protein doesn't spin. It's not an enzyme. It's just letting the protons flow back into the matrix. So because it's not capturing any energy from the gradient, all of the energy leaves as heat. If none of it is captured, then all of it can leave as heat. Can you think of why? So as this proton gradient diffuses back in, obviously it doesn't want to do this all over the place because it still needs ATP synthase to make ATP, but it can open up a few uncouplers to allow some of those protons to flood back in without actually capturing any of the energy. And so because the energy is not captured, it as the proton gradient diffuses back into the matrix, that energy is instead all released as heat. Now keep in mind, a lot of energy is released as heat through ATP synthase as well. I said earlier, ATP synthase captures a little bit of that energy to make ATP. At the end of the day, most of it leaves as heat. But this uncoupler is allowing all of it to leave as heat. What would be the advantage of an organism opening up some of its uncouplers and allowing massive amounts of heat to radiate out from the cells? I'll let you think about that. But yeah, that's really all I want to say for now about the mitochondrion.